Taylor polynomials are the polynomials that we've been working with that have been used as approximations for the function y equal f of x. A Taylor polynomial will agree with the function's value, the first derivative at the point, the second derivative at that point, and as you go with higher and higher degrees, it's going to always agree with that nth order derivative. Now, we had our second degree polynomial, p2 of x, which is our Taylor polynomial degree 2. We had it was f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. If we wanted to extend that now to a third order polynomial, we would start with that one. The nice thing about these polynomials, they're built on top of the previous ones, so that you're just adding an extra term then to make it a higher degree. So the third order polynomial would actually be f of a plus f prime of a, x minus a, plus f double prime of a over 2, x minus a squared, and then plus some c3 times x minus a cubed. Now, we already know that the polynomial degree 2 here matched the function's value. So f of a was p2 of a, and it's going to then be also p3 of a. Now, the reason I can tell easily, because if I evaluated this thing at a, this last term is just going to be 0. Having that term, the x minus a cubed, is just going to make that term 0 as you plug in x equal to a. So we can see that p3 of a is also going to agree with the function's value. F prime of a agreed with the derivative of a. Now, if you took the derivative of f of p2, you're going to still have some x minus a's left in this last term. Likewise, let's go ahead and take the derivative of p3. If I have p3 of a, p3 prime of x, this term's going to have a derivative of 0. This one, the f prime a times x, has a derivative of f prime of a. This one I need the power rule, so I'm going to multiply my 2 in front. So I'm going to have 2 times f double prime of a over 2, and then x minus a to the first power. And then I'm going to have plus 3 times c3, x minus a to the second power. Okay, I can see here now that p3 of a, the derivative of it, when I plug in my a, this last term is going to be 0. So it's still going to agree with the function's value, the derivative of the function's value, just like the p2 prime did. Okay, let's take the second derivative now. p3 double prime of x, the derivative of this one will be 0. This one will have derivative just f prime of a, f double prime, that is a single prime there. No, it's a double prime. F double prime of a plus, and now the derivative of this last term, I'm going to multiply the 2 in front, so I'm going to have 3 times 2, c3 times the x minus the a. Okay, and I can see if I plug in x equal to a, right here, I'm going to have that p3 double prime of x, when I plug in x equal to a, p3 of a will be equal to f double prime of a. So it agreed with the function's second derivative as well. And so now, finally, p triple prime of x, the derivative of this one's 0, the derivative of this one, here's our only x term, so the derivative is going to be the 3 times 2 times c3, but I want this to agree with the function's third derivative at a. So let me go ahead and plug in x equal to a. I'm going to have that p triple prime of a is equal to 6c3, and I want that to be equal to the function f's third derivative, which means that the c3 that we're going to use when we define this third order polynomial should be f triple prime of a over 3 times 2 Okay? So my third order polynomial, Taylor polynomial then, will be P3 of x f of a plus f prime of a times x minus a plus f double prime of a over 2 x minus a squared plus f triple prime of a over 3 times 2 x minus a cubed. Now, if you notice the pattern here, the number that's on the bottom is actually building the factorial, so that if we look for the nth polynomial, it's going to start the same way, and the nth order derivative of a over n factorial is going to be the coefficient of that nth term. And that's what this says. Taylor polynomial. We've got a function f that has derivatives defined at a. The nth order Taylor polynomial with the center at a, we're going to denote it by p sub n. It has the property that it matches the function's value, the first order derivative matches, and up to the nth order derivative matches the nth order derivative of the function. Now, notice this little parentheses around the n. That's referring to the nth order derivative. Now, the nth order Taylor polynomial is given by this right here. And that's exactly what I just finished writing down. Okay? And if you want to write it using summation notation, you could write it like this, where we're using c sub k's for the coefficient, but then just emphasize that the c sub k's then are the kth order derivative over k factorial of a. Okay? So now that is the Taylor polynomial. So let's see if we can construct a Taylor polynomial. I want to find the first order polynomial, the second order polynomial, up to the seventh order, p sub 7, for the function f of x equals sine of x. So I'm looking at the sine function over here in black, and I want to center it at 0, so I don't have to worry about x minus anything, it's just x. Okay, I'm going to go ahead and write out what the seventh one's going to look like. P sub 7 of x is going to be f of a, which is 0. This is my a. Plus f prime of 0, and then x minus 0, so times x. Since my a is 0, it's just times x, plus f double prime of 0 over 2 x squared, plus f triple prime of 0 x cubed over 3 factorial, plus f fourth order derivative. Now this is where it gets ridiculous, so that's why they just start putting the parentheses with a number in it. So that's the fourth order derivative at 0, x to the fourth over 4 factorial, plus the fifth order derivative of the function at 0, x to the fifth over 5 factorial, plus the sixth order derivative at 0, x to the sixth over 6 factorial, plus f to the seventh of 0, x to the seventh over 7 factorial. So the polynomial's order, it's not always the same as the degree, so be careful. The order matches the order of that derivative. Okay, so now let's see what these values are. The easiest way to do this is to go off to the side and write down what your function is and what some of its derivatives. F of x is equal to sine of x. F prime of x is equal to cosine of x. F double prime of x is equal to negative sine of x. F triple prime of x is equal to negative cosine of x. I need to go all the way up to seventh order derivatives. The fourth order derivative of x will be negative sine, so it's going to be back to sine of x again. F5, fifth order derivative, will be cosine of x. Notice we're starting to repeat ourselves. F6 will be negative sine of x. And F7 will be negative cosine of x. And I see 8 is going to be the same as the first one was. Okay, so now those are the f derivatives of x, but I need to always plug in the 0, whatever the a is. So now f of 0, f prime of 0, f double prime of 0, f triple prime of 0, fourth derivative at 0, do all these at once, it makes it a whole lot easier. Put in the 0 into the f, and you get sine of 0 is 0. F prime of 0, cosine of 0 is 1. Minus sine of 0 is 0. Minus cosine of 0 is negative 1. Sine of 0 is 0. Cosine of 0 is 1. And we know we're just repeating the same values over and over. Okay, so now those are the values I'm going to plug in for f of 0, f prime of 0, f double prime of 0, f triple prime of 0, and so on. Okay, so my seventh order polynomials. Now the nice thing about this is if I get the seventh one, the sixth one is just going to be breaking it off sooner. So let's just go ahead and build them up from the bottom now. P of 0 is just going to be, let's see, they didn't ask for P of 0, they want P of 1, so this one. P of 1 is going to be f of 0, which is 0, plus f prime of 0, which is 1 times x. P2 of x will be the first three terms. So I'm going to have 0 plus 1x plus f double prime of 0, which is 0. And I'm going to go ahead and just put the 2 there to emphasize that it's in the formula. P3 of 0, so P3 of x, will be these three terms plus the next one, the third derivative at 0, which is negative 1, x cubed over 3 factorial. And now the next one, P sub 4 of x, will be 0 plus x plus 0 x squared over 2 minus x cubed over 3 factorial. And now it's going to be plus the fourth order term. The fourth one is 0, x to the fourth over 4 factorial. P sub 5. Okay, let's go ahead and simplify these. There's x. X, again, notice P1 and P2 are the same. Then we have x minus x cubed over 3 factorial. But then P4 is the same. Okay, P5 of x will be x minus x cubed over 3 factorial, but I need to add the fifth term. The fifth term will be a plus the fifth order derivative at 0, which is 1, x to the fifth, I'm adding this term right here, x to the fifth over 5 factorial. And notice the sixth order derivative is just going to be adding this term, which the sixth order derivative at 0 is 0 again. So P6 is going to be identical to P5. But I want you to, I'm going to emphasize this. I would be adding the sixth order derivative, which is 0, over 6 factorial x to the 6th. But it still does come out to be the same thing as the previous one. Okay, P sub 7 of x. Now I'm going to start with what I just had for the sixth one. But now I have to add the seventh term, which is plus the seventh order derivative is negative 1, x to the 7th over 7 factorial. Okay, Okay, and that's all the ones they've asked for. Now notice that P1 and P2 are the same. And this is where I want you to note something really important here. The Taylor polynomial degree 2 is this one, which is the same as the Taylor polynomial degree 1. Okay? Just so happens they're the same, but you can't tell the difference. So if I just wrote down P of x equal to x, you wouldn't know which one it was. You wouldn't know if it was the first or the second order derivative in this case. Likewise, P3 and P4 are the same, so you don't know when you look at this whether that's the third or the fourth order Taylor polynomial. So you have to be really careful here. You need to understand which polynomial you're actually getting to know which order derivative you actually included. See, the fourth order polynomial includes that fourth order derivative here, whereas the third one didn't. So just be real careful. When they tell you the order of the polynomial, that's not the same as the degree of the polynomial. See, those are both degree 3, but the order of the polynomial is order 4. Okay, so the big difference there on the order, it will include that order derivative. That particular derivative, that fourth order derivative, just like the sixth one will include the sixth order derivative term, even if it comes out to be a fifth degree polynomial. So these two polynomials are the same. Those aren't the same. These two are the same. This one is the sixth order polynomial, but the seventh, where'd it go? Oh, here it is right here. These two are the same, but one of them's the sixth order polynomial and one of them's the fifth order polynomial. So just this is the fifth order polynomial and it's degree 5. This is the sixth order polynomial because it included that sixth order term when you were calculating it, even though it's a fifth degree polynomial in this case. So the degree of the polynomial is not necessarily the same as the order of the polynomial. Notice here, as you continue to go up, all of these polynomials only have odd terms. Now, you remember the sine function? This is an approximation for the sine function. Remember the sine function is an odd polynomial? The approximations will only contain odd terms. Okay, I do want you to look at one thing, though, before we quit this section. We're centering this thing around 0 right now. If I look at the first order approximation, that's that line. The third order is that cubic equation. That's the third degree polynomial, third order polynomial. And that, notice how it approximates it better as you get further away from 0. See, the first order one was just close, real close to 0, but the third one is actually better further away. The fifth order one is even better. It's better all the way out here. I mean, it almost coincides all the way out to that, past negative pi over 2 and pi over 2. And the seventh order polynomial is going to even be a better approximation, further away. It gives you a wider interval that it's approximating well. So you can see that the higher order derivative is an approximation for a larger interval around where it's centered.